Good evening to Doctor. I am Hui representing Group 6. So in this video, I will present Part A Task 3, which focus on proportional controller design for third order control system. So the objective of this task is to determine the proportional gain K that achieve approximately 20% of overshoot using three different design methods, which is the first one, try and error method, try and error simulation. Second one, the analytical approximation, and also the third one, rule Rotter's method. So uh, the plan considered in task 3 is a third order system, which is GS is equal to 1 over S plus 1 times S plus 3 times S plus flight. So a unity negative feedback configuration with a proportional controller is used. So due to higher order nature of system, so different design method may produce different time or result. So now we are going to show the first method, try and error method simulation. So this is a code we are using. And then after we put inside the MATLAB and try to run, so because the process is kind of long when we wait for it to be running, so I make it run first, and then this is the result coming out, and also the graph. So in method 1, a range of proportional gain value is tested using the MATLAB simulation here. So the overshoot is calculated using the step info command, and also the gain is produced overshoot close to 20% right here. And also after we run the code, here is the figures that are being generated. So firstly, it shows the overshoot, whereas the approximate uh, proportional gain K. And also here, the step response, and also the final step response. So Mm, using this method, the selected gain result in the overshoot approximation of 17.04%, which is reasonably close to the design target. So in this case, if we want to see the peak response, rise time, settling time, transient time, and or steady state, so we just right click and then put in the characteristic, and it will show on the graph. And then just like being mentioned just now, it shows the overshoot or approximate to 17%, so which is reasonably close to the design target. So this is the method 1. For method 2, analytical method. So in this method 2, the system is approximated as the second order system using the dominant pole assumption. The damping ratio corresponding to 20% overshoot is firstly being calculated using the standard overshoot equation. And then the coefficient matching is then being used to compute the proportional gain analytically. So as we shown inside this MATLAB, so as usual, I run the code first. Then this is the result coming out. So it shows the overshoot is 45.05%. And also here is the cursor pose. And then let's look at the graph. So here, after I put the, here it shows the overshoot is equal to 45.1%. So this analytical method result in the overshoot of approximately 45%, which deviates significantly from the target. So why does it happen? So this happens because the plant is third order, and the second order approximation doesn't accurately represent the full system dynamic. So the overshoot should be varying very differently. So it does very big difference. So this is for the method 2. In method 3, the root locus of the open loop system is being plotted. So as we show inside the graph, so this is the outcome being plotted by the MATLAB. So a constant damping ratio line corresponding to 20% of overshoot is overlaid using the script command inside the MATLAB. And the proportional gain selected at the intersection, here is the intersection of the root locus and also the damping ratio line. The root locus and also the damping ratio line. So we select the intersection point, we click, and it will come out with the graph of unit step response with selected gain k equal to 31.534. After we click this, we select the characteristic peak time response, peak response, and then we observe. So the overshoot is 18.2%. So it's very close to the design target. So the selected dominant pose accurately reflects the system behavior. So that's all for method 3.
The result demonstrates that for high-order system, analytical second order approximation may lead to inaccuracy prediction. Stimulation on based and configure methods such as try and error and low locus are more reliable as they consistent the full system dynamic. The root locus method also provide variable insight into stability and force movement. In conclusion, task 3 highlight the importance of selecting appropriate controller design method based on the system order, where analytical methods are useful for theoretical understanding. The low locus method provides the best balance between accuracy and insight for high-order systems.
Assalamu alaikum. This is Irfan Nawaz Nabil. So I will be discussing the part B of the project. So in this part of the project, we apply frequency domain analysis to evaluate the stability, robustness, and the steady state performance of three unity feedback control systems G1, G2, and G3. So using both plots, we determine the gain margin, phase margin, gain crossover, and phase crossover frequencies, and then relate these results to system type and steady state error characteristics. So here figure 1 to 3 shows the manual board plots, whereas figure 4 to 6 verify the results using MATLAB's margin comment. So let's see the code first. Here is the overall code for all three systems G1 to G3, and here are the system specifications in the comment window, where we can see the steady state the manual calculation and the verified calculations and the steady state error constants parameters. So let's start by explaining the graphs for system G1 uh, through graph figure 1 and figure 2. So in figure 1, we can see this is basically a type 1 system because there is only one pole in the origin. And from here we can see the magnitude plot shows a negative 20 dB per decade slope at low frequency, confirming the integrator, and at high frequency the slope steepens due to uh, additional poles at negative 20 to minus 40 radian per second. So from here we can say that G1 has a positive gain and a phase margin, so it is quite stable system, and the moderate phase margin indicates reasonable robustness but limited tolerance to error delay. uh, and we can verify our manual calculations from figure 4, which is here, and we can almost see very less amount of errors in compared to our manual calculations. So now let's jump into system G2. So we which are the plots 2 and 4. So here we can see all the stable margins and characteristics. So when we analyze systems 2, we can see there is no pole at the origin, making it a type 0 system. And the margin verification using the margin command plot confirms the large gain margin and phase margin matching the manual reading. So from this system we can say G2 is very stable and robust system with high tolerance to gain variation. However, type 0 it has finite position error constant kp, no non-zero steady state error to step input. So this shows the classic trade-off between the robustness and steady state accuracy. So coming up next, the system G3. This is system G3 from figure 3. We can see the characteristics here. So all the gain margins, phase margins, and other parameters are given. So here we can see it is also a type 1 system because there is a 0 at negative 10 radian per second. Okay. So from the manual board plot we can see a low frequency slope again confirms one integrator, and 0 introduces phase lead, partially compensating for the additional pores, and the phase curve drops towards negative 270 degree, but more gradually than the previous system G1. So from system G1 and G3, we can interpret that the 0 improves stability and phase margin, making G3 more robust than G1. Like G1, it is type 1 as well. So 0 steady state error to step input, and finite velocity error to constant kV. These demonstrate how zeros can be used to shape the frequency response and improve the robustness. So last but not the least, uh, from the system type analysis, G1 and G3, we can say both a type 1 system, which has finite kV, zero steady state error, and whereas G2 is type 0 system with finite kp and non-zero steady state error to step input. So these results directly align with the DC gain and error constant calculation performed using the function DC gain. So yes, that's all from my side.